This is the video solution for exam 3, Dynamics. And this first problem was a cam, and the way cams work usually is we have something that's round that spins or something that spins in around a fixed axis or a fixed point, and it causes something else to move in a linear fashion. So in this case, the round part rubs against this part and tries to move this cam part back and forth. So what we have to do, what we're looking for, is the speed and acceleration of this guy, and we had to find this distance here, this distance x, as a function of theta. So that distance x has this fixed part of 0.15, that's the radius of the circle, and then there's the radius of this part of 0.12, and the variable part is that sine theta. So this is what we came up with for the definition of x. Then we have to take the time derivative twice to get the speed and then the acceleration. And then when we plug these numbers into our equations, we get those two answers: 0.52 meters per second in the positive direction, but it's actually slowing down at this point, so I'm getting a negative 1.18 meters per second squared for the acceleration. This next one was an F equals ma problem and a conservation of angular momentum problem. So the F equals ma part is that when you spin something around in a circle here with a string, you're going to get some tension in that string, and the tension is an NTB problem. So I could find some of the forces normal is mass times acceleration in the normal direction. So the only force in the normal direction is the tension, and that's going to be equal to mv squared over rho, and you get 8.33 newtons. Most of you got that. The conservation of angular momentum part says that as this rotates around in this, and then if you pull in on the string, you have a new diameter or new radius, and but MVR1 is going to be equal to MVR2. That was the conservation of angular momentum. The reason that works is because the work you're being put into the system is only in the normal direction. There isn't any work in the tangential direction, so that says that the conservation of angular momentum works. So we get our new velocity at the inner diameter of 15 meters per second, and then we can do the same process here to find the tension. All right, the next one is was the instantaneous center problems, and a lot of you had trouble with this, but what you have to do is identify the velocity vectors. That's what you have to do first, the velocity vectors, and then draw perpendicular lines from those known velocity vectors to find the intersection, and that's the instantaneous center of zero velocity. So in this case, this guy is rotating around this point. The velocity of b is going in that direction. Draw a perpendicular line. I know the instantaneous center then is going to, of this length, the instantaneous center of this length is on this line someplace. So I draw that velocity vector. That's being pushed up, and then I draw a perpendicular line to that velocity vector, and we get IC. Do the same thing here, making sure that we draw the velocity vectors and perpendicular lines, you get an IC. This one is a little more subtle, that this wheel is rotating in this direction, which means it is actually moving in this direction. It's rotating in this direction, moving in this direction. So you can put a velocity profile here. This is the, if you will, the instantaneous center of the wheel. It's not the instantaneous center of this link, and that's what we were looking for, is the instantaneous center of this link. But at any rate, we can identify that the velocity of c is going in this direction, and the velocity of b is going in that direction. Drawing perpendicular lines, we can see that there is no IC. This one, we got this round thing going this way, and so the velocity of c has to be going straight down. B, this point B, rotates about a. So we know that the velocity is someplace in a circle like this, and the velocity then has to be perpendicular to the line connecting A and B, so that's the direction of the velocity of B. And in that case, we draw perpendicular lines from their known velocity vectors, and we find that they intersect right there at B, which means that B is the IC. And what do we know about IC? That's the instantaneous center of zero velocity, which means that at this point, B isn't moving. The next one's is the gear ratio problem. Fairly straightforward here, in that if you can find the velocity of A here, that belt isn't stretchy, which means that the velocity of C and the velocity of A are going to be equal to each other. This thing is now pulling this in a counterclockwise direction, so we have omega CDs going in this direction. And so I know that the omega of the outside is going to be equal to the same as omega of the inside, so the velocity of D is going up at point D, which is going to pull that velocity b up like that. So a couple of just key understandings is this thing rotates this rotates this way, pulls that guy up. So then we just put the gear ratios in. Velocity of A is equal to its r omega, which is 5. Velocity of A and velocity of C got to be equal to each other. Velocity of C is going to be equal to its r times this omega over here. We find a new omega over here of 33. Then the velocity of D is equal to velocity of B, which is equal to that little r right there, times it omega, and we get 2.5. Okay, this next one was a solved by any method that you choose problem. What we're looking for is a couple of velocities and a couple of omegas. First thing we were looking for is that you notice that this thing rotates in this direction. The velocity of C has to go in that direction. So velocity of C identified as 5 is an important understanding. Actually wasn't asked for, but you can't really solve the rest of the problem without doing that first. And over here I solved using the instantaneous center method. So first of all, I have to identify the velocity of B. Again, kind of from our previous problem, we could say that the velocity of B is going in this direction. Draw perpendicular lines to the known velocity vectors. And this is slightly different in that the wheels have got a different orientation. But anyway, perpendicular lines to those known velocity vectors, we can find the instantaneous center. This is a fairly symmetric problem in that this is 1 and 1, so that's 45 degrees, which means that that's 45 degrees. If that's 45 degrees, that's the length is 1, that length is 1, this is 1.14, and then this is 1.414, then this is 1.414. Again, so proceeding along with the instantaneous center, velocity of C is now equal to this length times this length here times this omega, and I can find the omega of BC is equal to 5, which is the same as the omega of that guy. Then velocity B here is going to be equal to this length times the same omega. So 1.414 times omega of 5 is equal to the velocity of B, and that's what we got, 0.707. Then the velocity of B here is going to be equal to this length times this omega. And again, 1.414 divided by the velocity of B, and I get the omega of AB, which is what we're looking for here, is equal to 5. We can also use the relative equation approach, and that's what I've done over here. Very few of you did it this way. In fact, I'm not sure anybody did it this way correctly, but you can use the relative equation approach. Again, you still have to identify C going in this direction as negative 5i. You still have to understand that velocity of B goes in this direction, but it's got a cosine 45 and a sine 45 going in those directions, and that's what the velocity of B looks like as a vector. Just plugging things into the vector equation, the velocity of B is equal to the velocity of C plus omega cross r of B with respect to C. B with respect to C is going to be, if you're standing on C, then B is going to be in the negative direction, negative I direction of negative 1. So that's what that's all about. Anyway, just keep on proceeding through the cross product, combining equations and combining terms, and you get those answers. Okay, the next one is a scalar gear problem. You don't have to use scalar, but it's the logical and easiest way of going through here. If you're pulling this spool in this direction, or this gear on this rack, it's going in this direction, then the whole thing is going in this direction. The velocity of G is going in that direction, the omega is going in that direction. We demoed this. And so if you do that, you can find that the velocity of E, which was given, is 0.1. It's going to be equal to its r, that little r right there, times omega. And then we can find omega is 0.4. Velocity of G then only goes in a straight line in the I direction, so that's going to be equal to 0.2. Then the velocity of C now has two components. It has the velocity of G plus the velocity of C with respect to G. And we just add those in. If G wasn't moving, it would only have rotation in this direction, which means that the velocity of C with respect to G is only in the negative J direction, and we just add those up. All right, this next one is the friction problem of a car. We've done a couple of these before, but I suggested it was constant acceleration. There's no aerodynamic effect, so fairly straightforward. Just find the acceleration using any of the conservation or any of the constant acceleration equation techniques. And so the first one, v is equal to at. Second one, v squared is equal to v sub 0 squared plus 2as, or s is equal to 1/2 at squared. Any of those work. The weird part is that given the things that I set up in the problem, you get different answers for these things. The reason is because these are not 100% consistent. And I think you'll find that in reality things are not always 100% exactly constant acceleration. We are simplifying this problem to say that it's constant acceleration, but it is possible to get these numbers, 44 meters per second, 61 meters in 3 seconds, to have those all be the same, but that would mean that the car wasn't exactly going in constant acceleration. But what we're doing is simplifying this thing, so I will accept any one of those acceleration answers. Then you do some of the forces in the mass times or some of the forces in the x is mass times acceleration in the x, and they can solve that for mu in one of 3 ways, and all of those, any of those would be okay. Then this next one is an angular acceleration problem, angular acceleration equation, and that's really the only good, easy way to do this one, and that's using the angular acceleration vector equation of acceleration of b is equal to acceleration of a plus alpha cross r of b with respect to a minus omega squared r of b with respect to a. Now I didn't put these on here, but these are all vectors, and so you need to kind of bear in mind that those are all vectors, meaning all have I and j components. And I gave you that the angular speed, or the omega, which is also something I didn't actually put on here, so let's just put omega there. The angular speed here was equal to 2 radians per second. The acceleration of a is given. Acceleration of b we know only goes in the x direction because it's constrained to move. It's only going to go in the x direction. Anyway, you put all those things in here. The alpha, as I've given here, is a positive k, meaning counterclockwise for our cross product. With respect to the r of b with respect to a position vector, if I'm standing on a, which way am I going to get to b? Well, I'm going in the negative j direction and the positive i direction. It is a 3, 4, 5 triangle, so it's fairly straightforward to just put that in there. Anyway, so you put all those things in, do the cross product, separate the i's, separate the j's, and you get 2 equations, 2 unknowns that you can solve for. All right, this next one, worth a little bit more. This was the statics problem to start with. What is the tension in this thing before you let it go? A lot of people missed that. But basically, there's a reaction here at O, both in the y and in the x direction. And some of the moments about O at the statics part is equal. You got that plus that minus this times that length, and you get tension is equal to 16.7. The dynamics part is some of the moments about O is equal to IO alpha. And so here the parallel axis theorem would be a good process of finding the instantaneous center, or finding the mass moment of inertia about point O. And so we'll have 2/5 mr squared plus md squared. And we're going to move it that whole length from its center of gravity to the point of rotation. Now the rod is modeled as a thin rod. This can be modeled either with 1/12 ml squared plus md squared, or it can be modeled as a 1/3 ml squared about that point. And so that's what I did here. Adding those things up, we get the I about O is 3.747 kilogram meter squared. Plugging that into then to our moment equation, and we get angular acceleration of 13.34. Then the last one was actually the most complicated one, the most involved one anyway. And here what we're looking for is how much force can you pull on this thing before you start lifting up the front wheel. That's the main thing we're going to go. And right before we lift up the front wheel, B actually goes to 0. So what we're looking for is the maximum force you can pull without B going to 0, or at the point that B goes to 0. It is not a tipping over backwards problem. It is not a slipping off the back problem. It is only an acceleration problem in that direction. So there's more than one way to solve this. I solved it by finding the common center of gravity for the load and the wagon together. So the load I divided up into 2 pieces, and so that this was the same area as this one, and they each weighed 40 pounds. The wagon weighs 50 pounds with its center of gravity there. Built a little table, and I found that x bar is equal to 2.038, and this is all from the reference. So there's my x bar, 2.038, and y bar is 2.077 from that reference. with that, then I can move on to a moment equation. And I just did one equation, I did a moment equation. Sum of the moments about A is the sum of the mass times acceleration times y bar. And I calculated my y bar here for, I calculated the y bar and the x bar for this moment equation. So the moment is, I have the, let me just put a CG in here. Let's change the colors here. Let's just say that the CG for the system is right there. And it's going to have an mg going down times an x bar, and it will also have a y bar that looks like that with a mass times acceleration vector. Mass times acceleration vector going in that direction. All right, so I didn't draw those on there. I probably should have. But anyway, so when I do that, I get mg, which is the total mass, or the total weight, if you will. So that's 130 pounds times the x bar. The pulling force has a sine component. Has a sine component going up this way, and this is the lever arm for that. It'll have a cosine component going this way, and this is the lever arm for that. And that's what these two are all about. Now the mass times acceleration vector is going in this direction, and it is going in the, what I defined as positive was in the counterclockwise direction, which means that this mass times acceleration vector is now in the clockwise direction, which means that it has to be negative over there. Adding all those things up, you get, and then you have to have the force equation. The force equation is sum of the forces in the x is mass times acceleration in the x. The only force I have in the x direction is this p cosine right there, the pulling force right there. Putting all that together, and I get two equations, two unknowns, and I can solve that for the acceleration and the pulling force. Now, there's another way to do it, or there's actually more than one more way, but another way I did do it was to treat all of the masses individually. And again, I divided it up into three pieces, so I called this one mass with its centroid up there, called this another mass with its centroid there, and this another mass with its centroid there. And you can see down here the results of that. Some of the forces and the sum of the moment equation is, or some of the moment equation is quite a bit more involved. You got quite a few more terms. You got three masses, and then I have three mass times accelerations on the other side. The answers turn out to be the same, which is handy. The pulling force equation is going to be the same. But anyway, you can walk through this if you wish, and compare your answers. Several of you also split the masses up into slightly different ways, and you can do that. Some people, let's go back here. Some people divided it up like this, and so this was 30 pounds on this side, and then this whole piece down here was 50 pounds. You can do that as well, and that would have, and then use three pieces, or you could do it all as one total mass times acceleration, or one CG using this technique, but those three, dividing that up is slightly different. Anyway, there's more than one way to do it, and I hope this helps.